Okay, all right. Is the audio quality decent, guys, at home? Someone will write in the chat. We have 4. I have 1 concurrent viewer from home, and I guess that most of you will be attending in, say, offline, so to say, because I have been notified that there is an issue with a timetable clash with the course of Professor Oriolo, which doesn't seem to be solved. As I mentioned before, the reason of this clash is a wrong setting made by someone years ago on GOMP that marked this course as the course of the first year, while it is a course of the second year. And this has implication on the timetable. This is a bad side. The good side, however, the good side, however, is that we will solve this problem. And for doing so, I just need to know how many students that are following are of the first year. As usually I say that it's useless to take this course on the first year because it's like doing analysis 2 and analysis 1 all together. No, you do first 1 and then 2. But I have to comply with the definition of the GOMP. So said, the problems will be solved as long as I am sure that I satisfy the majority of the students. And so, presumably, in a couple of weeks, maximum, we will be relocated in a new lecture hall and having no timetable clashes, okay? Because this is what we would like to do. But I have to do this if I'm sure that I have no one of the first year which is following, okay? I mean, the message I can't say, but the message is clear. All right. There is Francesco that says that the chat has some delay with live. Yes, I know that the chat has some delay because in order to allow even people that have a non-fantastic internet connection to stream and watch a video with a decent quality, my computer, when streaming, performs a compression of the stream. Compression means that it takes a temporal window of data and tries to make it small. And this introduces a delay. The delay is typically of 5 to 10 seconds in the chat. The delay that I see is longer. The delay that you see is longer because you write a message in the chat, it arrives to me, and then it has to come back to you, right? For those at home. Now, saying these administrative things, please enroll the form so that we know which students we have, okay? Please, 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 because we will take our decisions based on the enrollment, okay? Barbara, if you can quickly have, Barbara is for sure watching, so if you can quickly have a look at the enrollment thingies, the enrolled students, you can tell me, we can figure out how many are of the first year and the second year and where they come from in terms of study plan. All right, so now this was bureaucracy, and then let's go to the meat. So we will today talk a little bit, give a very short introduction of most of the things that you have to know about probabilities. It's a very quick lesson, and I hope that at the end of it, you will not dislike probabilities as much as you used to do before of this course, if any, all right? Now, come on. Okay, this is the outline of the lesson, but I'm not that much discussing the slide of the outline. Let's start with an experiment. So let's start, last time we have encountered a funky robot, Orazio, right? Like this ugly robot with 2 wheels made of wood and so on. That, in this case, we even simplify our domain by discretizing Horatio, discretizing this robot, and making this robot moving in a world that is a grid world, which means that it can take one position in a grid, right? Like a checkerboard. And also, the controls will be go up, go down, go left, go right. In this building, we also put an access point, because the robot wants to be connected to Wi-Fi. Roomba is connected. I wonder why Horatio shouldn't be connected. And still, we're in the discrete domain. We measure the signal strength of this access point, something that you have on your mobile phones. When you go closer or further from the access point, you see these little bars. I have more or less signal, right? And let's say that we have a limited number of signal strengths. We discretize this domain. We can measure up to 4 signal strengths, so 4 levels of signal strength. Okay. Clearly from a given location, because we all experience that when we move in a place, like, oh, I don't have field, and then you move to another location and another location. All right. So said, this is the scenario. We want to do an experiment, and we want to monitor, to construct a statistics of the signal strength per location. We have a discrete number of locations because our robot is on a grid, and we just want to collect a statistic. So we take the robot, we put it in the first location, which is the corner high left, and we start acquiring data, right? With basically measuring the strength of the access point. And then we count how often we measure the signal strength of level S1, the signal strength of level S2, S3, and S4, right? Each time we measure a signal strength, we take a ball and we mark it into the corresponding bin. Okay? If from a location, for instance, we would only measure the signal strength S1, we will have all the balls sitting in this bin. Agreed? Now, we could then, for each, and we repeat this experiment for each of the locations, right? Then, for a given location, we can compute the statistics. So how often, out of the number of trials that I've done, the number of times that I was listening, was I measuring signal strength X1? Maybe in this time, in this example, is 3 out of 10. So 30% of the times I was measuring signal strength S1. How often was I measuring signal strength S2? 4 times out of 10, so 40%, and so on. This number, the number of the occurrence of an event, an event is like measuring signal strength S1, or measuring signal strength S2, the occurrence, the probability of the occurrence of an event in this approach is basically, can be reconstructed by the statistics, and it's the number of times where the event is true divided the number of times that something has happened, that I run the experiment. All right, this is something easy. And so we can then define a number which is associated to a certain event, which we could picture as if it was a histogram in general, or a function. What is the domain of the function? The domain of the function is whether S1 happened, or S2 happened, or S3 happened, or S4 happened, right? And the codomain of the function is a value which in this case spans between 0 and 1, right? Because in the most of the cases, all events, so only an event happened all the time. So I have n over n, okay? And we can call this number, we can talk about the probability that while being at a certain location, because each of the locations of the environment carries its own instance of experiment, right? So we repeat the experiment in every possible location in order to get a histogram which is representative of that location. And to each of these intervals, then we can assign a number to each, a function in theory, which is the probability that in the cell Lj, where Lj is one of the cells, the signal strength measured is equal to a particular value of signal strength. Great? Very good. So, of course, we change location and then we will have different statistics for a histogram that changes depending on where you are. Now, this was an example just to ground down and to provide you a visual experiment, a visual example, a simplistic visual world where you can picture what's going on and how the theory can be mapped to this simple example to provide you a more concrete grip on what's going on. Let's talk about the concept. You mentioned the concept event. What is an event? An event in probability is a statement that can be either true or false. Either something happens or it doesn't happen, right? But of course you don't know whether it certainly happens or certainly doesn't happen. Hence the probability value. The statement, the signal strength S falls in the interval, because remember that the signal strength is a continuous quantity, and in order to characterize it with 4 different bins, we had to select a range for the signal strength S1, a range for the signal strength S2, and so on. We had to discretize, right? Same as you do with the Z transform when you do the control things. Now, we could then characterize 4 disjoint events. What does it mean that 2 events are disjoint? That they cannot be true at the same time. So that the fact that one is true means that the other one is not. Okay? Disjoint. There is no intersection. And clearly there is no intersection because either the signal strength falls in this interval or it falls in this other interval, which is, for the way we selected the interval on the x-axis, is disjoint. Now, for simplicity, this S here is what we will call a random variable, which is a variable which we attach the probability distribution, basically. So, one of these histograms. And in order to avoid writing S equals Si, we will simply write capital Si. Okay? Just to denote this sentence. Agreed? Now, the probability that in a certain location the probability that a certain event, the probability that in location Lj the robot measures the signal strength Si is just a number. It's a number that denotes how likely it is that the robot, while sitting in that particular location, measures that signal strength. Formally, in general, a probability is a function which is going from each measurable subset of the event space omega to the interval 0, 1. Now, what does it mean, a measurable subset in this domain? Well, it's any combination of intervals that I can have. No? The first, I can define an event could be I measure signal strength S1 or signal strength S3. Isn't it an event? Yes, because it's a sentence. It can be either true. So this is a sentence which is true if either I measure signal strength S1 or I measure signal strength S2. Agreed? And what is the probability of this event? Well, the events are disjoint, and so intuitively it's the probability mass that sits in the event S1 plus the probability mass that sits in the event S2. Okay? And normally the probability of an event is a function that, the probability of something is a function that goes from each measurable subset of this domain omega. So you just have this volume, in this case is a line, but you could have any domain. Remember that the domain of a random variable is the space where the random variable can take values. So if we're talking about signal strength, the space is S0, S1, S2, S3, or S1, S2, S3, S4 in this case. If we're talking about distances, maybe limited maybe by a sensor capability, the domain of a distance measure is the distance between 0 and the maximum distance that I can measure. right? This is going to be the domain. And a probability in this case will be a probability defined from each interval of distances, or each set of distances, to a number, which is between 0 and 1. Okay? Now, so said, we can throw in the axioms of probability. The axioms in a theory are the basic truth that you assume are true, are valid, you assume hold. Once you have the axioms, so everything else in every theory follows from the axioms. Okay? And the axioms are quite straightforward. The first axiom is that the probability of an event, a general event, a sentence, where an event is mapped into a measurable subspace of the set of all possible events, is greater or equal than 0, obviously, because worst of the cases, something never happens. It can't happen a negative number of times. The second thing, which is quite intuitive, and we have seen it with the example of signal strengths, is that the probability of the union of a set of disjoint events, so I have a set of events, so imagine a set of regions in my domain, which are disjoint, which have no intersection. Clearly, the probability of an event, which is the union of these events, will be the sum of the probability of the individual events. Clear? The third axiom is that the probability that something happens is 1 in this closed domain. So once I measure the signal strengths, my detector, my sensor, either tells me 1, 2, 3, or 4, right? So the probability that I measure either signal strength 1, signal strength 2, 3, or 4, or either. So like one of the four, one of the four is 1 if I run once the experiment, which means I listen, I acquire one sample. Clear? All right. Barbara, ping me in case there are questions. All right. I have to, okay. Okay, now, this characterization is quite intuitive. This characterization is quite intuitive in case of discrete domains, right? This characterization of acquiring, of calculating the probabilities through statistics. What can we do in a continuous domain? Well, continuous domain, so if the domain of my random variable is continuous, like in the case of the distances, right? Well, the problem is that then I can't, so presumably every time I measure a signal strength, I will get a different value, presumably, because I have infinitively many digits, and it's very unlikely that I will get the very same number twice. Okay? So it's quite hard for me to calculate statistics. What I could do is to do a binning, as we have done before. But the binning doesn't really capture, it has a certain resolution, doesn't really capture the probability, the fact that the variable is continuous. I would like to be able to work with continuous variables. So if I would do so, everything comes, this issue comes from the fact that in a continuous domain, the very definition of an event is ill-posed, because in general, in a standard probability distribution, in the continuous space, the event, the distance measure will be exactly 3.5 meters, typically has a probability mass of 0. Okay? Because you have a continuous infinity of values that your generator can give you, and even if you get a lot of numbers around 3.5, we'll never get, or very unlikely, infinitively unlikely get 0.1, unless of the generated probability distribution, for instance, if you have a Dirac centered in one point. But this is another story. All right? So it comes from the very definition of event. But there's something that you could define still leading to the continuous domain, which is assuming that we're dealing with a continuous domain which is a unidimensional, so a line, right? A line, let's say, a line in the positive plane, so between 0 and infinity, or between 0 and infinity. In this case, we could define, or between minus infinity and infinity. In this case, we could anyway define an event just by partitioning these possible outcomes in two. We basically pick up a value, a distance, and we say, oh, what is the probability that the distance measured will be less than 1.5 meters? Okay, we can do that. And because there, this event will not have a zero probability. The event, anyway, is probability of measuring something less than something else. So we can define, therefore, in this context, the domain, the event that the random variable x, which is the value that we measure, is lower than a certain point on the axis that we select. Okay? So we defined events which are controlled by a continuous node. But they are no more disjoints, clearly, right? Because the probability that I measure a distance less than 1.5 meters will be somehow higher than the probability that I measure a distance less than 1 meter, right? Because I have 1 meter, because one event is contained in the other. No? So one is true, and therefore, but there is something we can observe, that these events in the continuous space are all contained one in the successor, right? The probability, if I have two numbers, the probability of x being lower than x1 has to be the event that x is lower than a certain value x1 is lower than the probability is contained, the event x lower than x1 is contained in the event x lower than x2 if x1 is smaller than x2. No? Because one event is contained in the other. The fact that two events, that we have a chain of events which are contained one in the other, allows us to define something which is the cumulative distribution, which is the probability of a random variable being lower than a certain number. And this monophonically increasing. Okay? Because it's formed by events which are by chain, one after the other, contained in the previous one. This is an example of a cumulative density function of events contained into, like a cumulative density function on a continuous space. So, it's a curve. Clearly, what is the, in general, what is the cumulative density of infinite? The value of the cumulative of P of infinite plus infinite. Exactly. Because the event, a number is smaller than infinite, basically contains all other events. Okay? Then therefore the function is monotonic, and this is an example of a density function. Monotonic means that it's constantly increasing. Now, the question is like, given this machinery, how do I measure the probability that an event or a random variable, the probability of the event that a random variable falls between an interval between the number x1 and the number x2? Well, simply, we can take the probability that the variable is in this semi-axis, right? And this is one event. It's a measurable subset. We take the probability that the random variable is in this interval, right? Then we have the two values. In order to capture this area, we just calculate p of x2 minus p of x1. So this difference here will be the probability of the event. The random variable x is in the range x1, x2. Okay? This is something which is also obvious, but allows you to visualize the fact that the issue that we have in the continuous space, we cannot count disjoint events, right? We can only take an event and subtract to the event another part. Okay? But then you tell me this is quite trivial because it's just an integral operation. What if instead of taking the cumulative density of a continuous random variable, I'm working with the derivative? The derivative is not of this function over here with respect to x, is nothing else than the density of probability in an epsilon in that particular point. Clearly, if I take the derivative, then through integration, I could cover any possible measurable subset. So let's define what we call a probability density, P of x, which is defined as the derivative of the cumulative density function. Observe that the derivative of a probability density, which we will write with small p of x, can be higher than 1, right? Its integral can't be higher than 1, but the function itself can be higher than 1. For instance, in order to represent the probability density function, probability distribution that expresses my absolute certainty that a variable takes a certain value x1 could be represented with a Dirac centered in x1, because Dirac is a valid probability density. It has integral 1, it's a density. If integrated gives me a step, which is monotonic, so there I go. Clear? So important, remember that the density, a probability density, can be high, because if it's very steep, the surface, but the fact that it's very steep means also a lot. Means that what is the probability density, the probability value of that I fall in a range which is between this number and, let's say, this number? Well, I would have to go here, pick up the two values, and do the difference. And so basically I'm already at 1, because it's very steep. All right, all that clear? Very good. Now, in general, if I have the density, I can compute the probability for a generic event that in this case, in the case of the continuous space, I could just imagine as an interval or a set of interval on the x-axis. If I have in a monodimensional space, if I have a two-dimensional space, an event could be any closed or even open, any measurable subplane, which I can draw also, like in a two-dimensional space. This could be an event, right? Which is an event which is true if a variable xy, in this case it will be a two-dimensional variable, falls into this ball over here, into this ellipse. Assuming that it can only fall in this ellipse in general. And this would be an event. I could also take two potatoes here, two regions, and say, I define an event, the fact that the variable either falls in this region or in this other region. If they are disjoint, I can also calculate easily their value, the probability value. I have to charge the phone. No, I can't charge the phone because I have all used slots. All right. Having said that, let's come back to our old exercise, which is the good old Horace. we can repeat another experiment. Let's say that we are not controlling our robot, right? We are just observing it. Maybe it's controlled by someone else, but it's a robot, so it's doing somehow some repetitive task. So we could conduct a new experiment that tells us wants to monitor the probability that in a certain location of the environment, Orazio appears. So basically, every second, we look in the space where the robot is located in that instant. And then again, and again, and again. So we will get what? We will get a probability distribution over the possible locations. In this case, in this 10 by 10 word, we could visualize it as a histogram of 100 numbers. Okay? So we count how often Orazio visits its location, we get something like that then in the end gives us a probability value. In doing this experiment, what are we guaranteed of? We're guaranteed that none of the cells will take a value which is higher than 1, right? Because every cell has the number of times that Orazio has been there divided by the times that Orazio has been somewhere. Not only will we also be ensured that the sum of all cells will be 1. Okay, because if I sum all the instances where it has been something, then it has to be equal to the number of instances of experiments that I put. All right? Observe that when we're acquiring the statistics about the location of my robot, we are completely ignoring the signal strength. It's a different experiment. The only thing is that the robot is the same, but it was a different experiment. Now, let me introduce the concept of conditional probability. What is the conditional probability? Well, the condition is what? It's something that controls the preconditions of an experiment. When we were conducting the experiment on the signal strength, given that by our gut feeling we know that the signal strength is correlated with the location, it depends on where the robot is, we say, hey, it's useless that I measure the signal strength everywhere because I will just get a meaningless average value. No? If I was a politician, I could use it, but I'm an engineer. So what I can do is to say bullshit, if I was a politician. What I can do, what we did actually is to conduct one experiment in a location. What was the condition of that experiment? It was the location, right? What was the condition of the other experiment? Location. What is the domain of a probability distribution of the robot of the signal strength? Is the signal of one of these experiments? Is the signal strength. On the x-axis, I only had S1, S2, S3, S4. Agreed? But I have many of them. In order to visualize, and many of them, one per each condition, one per each cell. You can visualize this as if you were observing a histogram of 4 values, and you had a knob here, una manopola, a knob. Turning the knob, you select location L1 versus location L2 versus location L3, and once you change the location, clearly the histogram changes. Okay? The knob that allows you to select the instance of the experiment. There is a way in the probabilistic formalism to express a conditioning. Before, we were just putting an LJ, Li here, right? But in the probabilistic language, instead of putting the L here, you put the conditioning event on the right, after a bar. So remember that when you see a probability distribution in this form, this is the domain where the probability distribution takes place, and these other here are parameters that control the particular probability distribution. Remember the lesson of last time when I was mentioning the probability of a measurement given the state. The state is controlling the probability distribution that you will be observing in the measurements. But the state acts as a knob. The randomness is easily modeled in the measurements. All right. Sorry, a second, because it's my third hour of lessons. Then let's also think about some more mixing the domains. So far we had the domain of location, domains of probability distribution. We had two experiments, one that tells us the signal strength given the location, and we had another experiment that tells us the probability of a location, and without anything, just straight, ignoring completely the signal strength. And if I give you a statement which is an event, I want to mix these two domains. I want to talk about a word, omega, a set of events, which is the cross product of the locations and the signal strength. So one value in this domain will be one possible location and one possible value of signal strength. Right? We could express the event measuring the signal strength S3 from location L2. This is one instance. One possible outcome of this thing, because from to describe deterministically one configuration of this simplistic word, I should say the robot is in this location and is measuring this. There's nothing else that I can observe at this point. Okay? So one event in this universe, so this universe spans in location and signal strength. So it's a cross product. You could visualize it as a matrix. No? Right. Or as a cube, if you want, because we organized the locations in a grid. But if you just see the locations as on an array of 100 components, and on this other part you just like put the signal strengths, you could see it as a table that has 100 rows, 100 columns, and 4 rows, corresponding to the 4 possible signal strengths. Now, if I tell you what is the probability that the robot is located in location L2 and from there senses the signal strength S3. Let's reason. When we were conducting the experiment on the locations, we completely ignored the signal strength, right? So the event I'm in L2 is certainly more likely than the event I'm in L2 and I measure signal strength at S3, because being somewhere and measuring something is more selective than just being somewhere. Right? Very good. But think about it. If I take, and I have another part of the experiment, which was the conditional probability. P of L2 just tells me how likely is that the robot is in a certain location. Okay? It acts as a discount factor, basically. It tells me it's one only if I only observe the robot there all the time. And if I tell you the fact that I consider this number here is smaller than 1, if this number was 1, which means that basically during a regular operation, I only observed all the time the robot in L2, it has never been anywhere else, then the probability of P of L2 will be 1. And then this means that of all experiments of the signal strengths, I would have only to consider, in order to tell the probability of observing the signal strength S3, the instance where I was in L2. So if this is 1, then basically this cancels, and this probability becomes equal to this probability, right? If I was never in L2, because I never observed the robot being there, then this probability here becomes 0, and so the probability of measuring S3 and being in location L2 is obviously 0, right? Basically, this is the game of the chain rule that acts as this discount factor. So I basically have, on the one end, on the right hand, P of L2, is the probability that the cause happens. The cause is being in L2, the controlling event. If the controlling event, assuming that the controlling event happened, but assuming that the controller, I already have discounted it by multiplying it by P of L2, then I can take the outcome of this experiment evaluated in the hypothesis of measuring the signal strength S3. Do you feel it? Or do you want, I will try to go on the blackboard if this thing, let's see. I don't know how to lift the blackboard here, but I will find a way. No. There's no way of writing the blackboard, I think, anymore. No. Okay, we have no blackboard. This is somehow terrible. There must be a way. No? Not cooperative. Well, sorry guys, I mean I will try to, there's no blackboard, there's not much I can do, but what I can do is to use paper. And I will put that screen on the screen. You don't see much. It's very hard. I will try. So, we have the probability of being here, or being here. Do you see? All right. Now, on the other hand, we have right? Let's think about it. We have the instance, this object over here represents the experiment of measuring a signal strength S1, S2, or S3 while being here, right? Now, it's quite obvious that the probability of being here and measuring the signal strength is equal to the probability of being here anyway and the probability of measuring the signal strength S2 while I was here. So you have to multiply the probability of the cause times the probability of the effect given the cause. Okay? But then we have another slide for that. Let's see. I will fix also the blackboard thingy. Don't worry. This one. 5. Not done. All right. So this object over here acts as a discount factor for the rest. Now, let's talk about joint probability distributions. I mean, a joint distribution is a distribution that unites two variables. One event of the joint probability distribution, for instance, signal strength and robot locations, was the ones that we have already decided. And we can imagine it as a grid like that. I have already mentioned it. Remember that all these are disjoint events because they can't happen all together. Agreed? Now, how do I obtain it? Well, first of all, let's visualize how we can represent one instance of the experiment on the signal strength. That was easy. We could visualize it as if it was a histogram, with 4 values. We have one of those for each location, right? On top, we could visualize the histogram of the probabilities over the experiment on the location. So here we'll have the probability of the robot being in the first location, second, third, fourth, right? What we want to obtain is having these two, this and this. But of course, we have one instance of this experiment for every possible cell. We could organize them into some sort of matrix. Huh? No one. And then applying the so-called chain rule, which is the rule that we have seen before, where you basically say that the probability that that an event A and an event B happen together is equal to the probability that the event A happens times the probability that the event B happens, given that the event A has already happened. Basically, visually, you take one probability that the robot is here, and you multiply this number by all this vector over here. This has the effect of discounting, basically, this entire line of the product based on the number, based on what? Based on the probability that the robot was really here. So what happens is that if you conducted your experiment and the robot was never here, this line here of the product will be 0. If the robot was only here and nowhere else, basically this line of the outcome, this column of the matrix, will be having the same value of the conditional distribution, which is this one over here. And in general, the matrix will be 0 everywhere else, because we said that the robot is only here. So we have 1 here and 0 all over. Once you do 0 times this, here you get a line of 0. 0 times this, you get another line of 0, and so on. Do you see that? You feel it, actually. That's what I'm interested in. Okay, so it's cool. We know how to calculate a joint distribution out of a conditional distribution and a conditioning distribution, let's call it this way, just by doing the product. All right. Once I have a joint distribution, if I ask you, how likely is it that in my domain I measure the signal strength S1? Because maybe I want to figure out whether I want to improve the access point, and I want to see if I have enough coverage in all the environment. And I ask you, hey, how likely is it that everywhere you measure the signal strength S1? Okay? Well, it's quite easy, because we have the joint table of events. So basically, this domain, the domain of the joint distribution, captures every possible outcome of the phenomena of the world where the robot can be somewhere and measure a signal strength. And then, in order to answer this question, I will have only to identify into this domain what are the values that correspond to the event measuring the signal strength S1. What will they be? Well, they will be all the events that are in this line over here, right? And what is their probability mass? Then you take all of them and you sum them up. And this gives us the rule of marginalization. So if you have a joint distribution means an end, you can calculate, you can marginalize out a variable simply by the probability of the event that is the union of all events where the variable S1 is true. It means that you have to sum all other events. You can delete basically Lj, L, from here, in order to delete, to flatten the distribution, along a variable. You just like sum over all possible values of that variable, and you delete the variable, right? You can imagine it as if it was a squeezing. Okay? Clearly, it looks like a projection operation. So you have a probability distribution. What does it mean, marginalizing? Well, marginalizing means ignoring a variable. How do you ignore a variable? Well, you have to basically squeeze this volume, squeeze this object, or to look at it from a side. But if you look at it from a side, you also have to consider how much probability mass you have in the potential occlusions of this solid. Anyway, in order to calculate the probability of the event S1, you simply sum over all possible events where the event S1 is true, which happen to be this line here. Okay? If I would be interested in calculating P of S2, I would have to sum up over all possible values over here. If I would want to have P of S3 the same, P of S4 the same, right? So I could calculate the probability distribution, not the event, the probability distribution P of S, simply by carrying on this operation for every possible element of the domain S. Okay? Which simply corresponds to a flattening of the thing. And this leads, for instance, to the game of marginalization. So if I want to delete this line, this dimension, I simply sum over that dimension. Clearly, the same holds in the continuous case. Instead of summing, you integrate. That's another thing. I think I will take a break after independence. I need a break for my throat. We take a break and I'll be back in 5 minutes. I will leave the stream running because otherwise I lose the connection. And if there are issues, you post them in the chat. I will just stop not the streaming, but the sharing. And then I put this. Ragazzi, se ci avete domande fatele, eh? Vai, vai.
Cioè, è giusto secondo te parlare di indipendenza tra variabili? In questo caso abbiamo diciamo due variabili, una è la S e una è la L, no? Però
Indipendenza non ho ancora parlato.
no, no, ma una cosa proprio così mia, cioè se noi dobbiamo calcolare P di L uguale 1, cioè lo calcoliamo diversamente da P di S uguale 1, perché per fare P di S uguale 1 dobbiamo fare tutta quella somma di joint probability.
Noi abbiamo fatto degli esperimenti, no? Abbiamo fatto degli esperimenti. Concordi che l'outcome degli esperimenti... Come ci arriviamo? Concordi che l'outcome degli esperimenti era ragionevole?
Certo.
Concordi, diciamo, la domanda che ti faccio è,